Propensity score weighting is a method for identifying the average treatment effect under the selection on observables and overlap assumptions. It proceeds by calculating a weighted average of the observed outcome y with weights w that depend on the observed covariates x and an individual's treatment status d. In particular, they depend on whether or not an individual is treated and the probability that a person with her covariate level will be treated, namely the propensity score, P of x. We'll prove this result in 3 steps. In the first step, we'll show that the conditional expectation of y1 given x is equal to a particular weighted average of the observed outcome y, where the weight is d divided by the propensity score, P of x. The second step is similar, but in this case we show that the conditional expectation of y0 given x can be written as a different weighted average of the observed outcome y. In this case, the weight is equal to 1 minus d divided by 1 minus the propensity score. In step 3, we'll combine the results of step 1 and step 2 to derive an expression for the conditional average treatment effect given x, namely the expected value of y1 minus y0 conditional on x. This step is mainly algebra. Finally, we'll use iterated expectations to convert the result of step 3 into the theorem we've set out to prove. We'll start by proving step 1. To do this, we'll rely on the fact that d is binary. In other words, it either takes on the values 0 or 1. This has a number of important implications. First, d squared is equal to d. Second, d times 1 minus d is equal to 0. Using both of these facts, along with our expression for y, the observed outcome, in terms of d and the potential outcomes y0 and y1, we obtain the following expression. Notice that the first term, d times 1 minus dy0, will in fact equal 0, while the second term, d squared y1, will simply equal d times y1. We've shown that d times the observed outcome y is equal to d times the potential outcome y1. This is our starting point to prove step 1. Substituting into the expression for the expectation of dy over p of x given x, we obtain the following. P of x is a function of x. That means that from the perspective of the conditional expectation given x, it's a constant and can be pulled in front, leaving us with 1 over p of x times the expectation of dy1 given x. Now let's take a closer look at the term in the blue box. Using the law of iterated expectations, we can rewrite this as the expectation of dy1 conditioning on both d and x. The outer expectation is taken with respect to the distribution of d given x. Now, because this innermost expectation conditions on d, we can pull d in front, leaving us with the product d times the expectation of y1 given d and x. To simplify this further, recall the selection on observables assumption, which tells us we don't need to condition on d after conditioning on x. This leaves us with an even simpler expression, namely d times the expectation of y1 given x. Recall that this outer expectation is taken with respect to the conditional distribution of d given x. Since the expectation of y1 given x is a function of x, it's therefore a constant from the perspective of this outer expectation and can be pulled out, leaving us with the product of two terms, the conditional expectation of d given x times the conditional expectation of y1 given x. Because d is binary, this first factor is equal to the probability that d is 1 given x, and that's just the propensity score. So we've shown that the expectation of d times y1 given x is equal to the propensity score times the expectation of y1 given x. Substituting this result back into our expression from above, we notice that the propensity score in the denominator cancels with its duplicate in the numerator, leaving us with exactly the expression that we set out to prove for step 1. Nearly identical reasoning allows us to establish the result of step 2. Again, the key is that d is binary. Whereas in step 1 we worked with d, here we'll work with 1 minus d. 1 minus d squared turns out to equal 1 minus d, and as we've already seen, d times 1 minus d is 0. Using these facts, we obtain the following result. Again, substituting our expression for the observed outcome y in terms of the potential outcomes y0 and y1, and noting that the term involving 1 minus d times d will equal 0. Now, substituting this result, we can calculate the expectation on the left-hand side of the equality in step 2 as follows. Because p of x is a function of x, so is 1 minus p of x. That means that we can bring it in front of this conditional expectation. If you know x, you know p of x, so it's just a constant from the perspective of a conditional expectation given x. Now we're left with the expectation of 1 minus d times y0 given x. Let's take a closer look at this term. Again, using iterated expectations over the conditional distribution of d given x, we can write this as the expectation of 1 minus d times y0 given d and x. And because 1 minus d is just a function of d, we can pull it in front of the inner expectation, leaving us with the product 1 minus d times the expectation of y0 given d and x. Recalling our selection on observables assumption, we can drop d from the conditioning set, and we end up with a product of two terms, the expectation of 1 minus d given x and the expectation of y0 given x, again using the fact that a conditional expectation given x as a function of x can be pulled out in front of the outer expectation. Because d is binary, the first factor is just equal to 1 minus the propensity score. Substituting this back into our expression from above, we see that the 1 minus p of x in the denominator cancels with a 1 minus p of x in the numerator, leaving us with exactly the desired expression. Now we're ready for step 3. In this step, we'll combine the results of steps 1 and 2 to obtain an expression for the conditional average treatment effect given x. This quantity is defined as the expectation of y1 minus y0 conditional on x. And substituting our results from steps 1 and 2, we obtain the following, namely, the conditional expectation given x of the difference dy over the propensity score minus 1 minus dy over 1 minus the propensity score. And the rest of this step is just going to be algebra simplifying the inside of the expectation. Putting these under a common denominator, namely p of x times 1 minus p of x, we can write dy times 1 minus p of x minus p of x times 1 minus dy. Again, this is just algebra, but simplifying the quantity inside of the brackets, we obtain d times y minus p of x times y, which is exactly what we were looking for. D minus p of x multiplied by y. Finally, we substitute this back into our expression above for the conditional average treatment effect, obtaining precisely the expression in the green box marked step 3. Now that we have an expression for the conditional average treatment effect given x, all that we need to do to prove the final result of the theorem is to use iterated expectations to average over the distribution of x. The average treatment effect, which is to say the unconditional average treatment effect, is defined as the expectation of y1 minus y0. And by iterated expectations, this equals the expectation of y1 minus y0 given x, which is precisely the expectation of the conditional ATE. You may be wondering where we used the overlap assumption. While I wasn't explicit about this, the overlap assumption is implicitly contained in several of the expressions on this slide. Whenever we write p of x or 1 minus p of x in the denominator, we require each of these terms to be non-zero. That's exactly what the overlap assumption gives us, and if we didn't have this, some of the expectations we're using to identify the ATE would fail to exist. In summary, propensity score weighting allows us to identify the average treatment effect under the selection on observables and overlap assumptions by calculating a weighted average of the observed outcome y with weights that depend on an individual's treatment status and her covariate vector x.